Okay, today's lesson should look pretty familiar to you. This is called the Pythagorean Theorem, and they throw in its converse as well. The Pythagorean Theorem is something that you probably learn in Algebra 1, if not even before that. And we've actually talked about it, I believe, a little bit in the beginning of this. I'm not really sure, but it was somewhere in the beginning of the book. We talked about Pythagorean Theorem, but this is the first time we've officially seen the Pythagorean Theorem. So let's take a look at when we use the Pythagorean Theorem. We use it on triangles that look like this. Let me put that little box right there. And so this is a right triangle. You only use Pythagorean Theorem on right triangles. Okay? So make sure that you don't try to use Pythagorean Theorem on an acute triangle or an obtuse triangle. It has to be on right triangles. So what we're going to do is we are going to label the sides of the right triangle. I'm going to call the legs of the right triangle A and B. The legs are the ones that are not the hypotenuse, okay? And the hypotenuse I'll call C. It's very important that you differentiate the difference between the legs and the hypotenuse. Now look, I didn't really have to call this A. I could have called it B. Either the legs, I could call it A and B. It doesn't make any difference which letter I call it. But according to our little theorem, our little rule that we're going to show, our little formula, it's very important that C is the hypotenuse. Very, very important. So C has to be the hypotenuse. So let's write that in there. All right. A lot of people get kind of mixed up, and this has to be a leg, and A has to be a leg as well. Now we have a little formula that we're going to use right here, and it's pretty simple. It's as easy as ABC. Watch. A squared plus B squared equals C squared. That's it. See? Just in order, ABC. Pretty nice and easy. Again, you're probably very familiar with this. It's probably not the first time that you've seen this. So what do? What does this formula say that we do? This is the two legs. So what I'm going to do is I'm going to square the two legs, and I'm going to add the two legs together. Well, if I do that, that's always going to equal the square of the hypotenuse. So if I take leg A and leg B, and I square them first, then I add them together. Don't add them first. Make sure you square them first. So square this, then add them together. It's always going to equal the hypotenuse squared. Now, I have students all the time saying, well, if that's true, does it mean that A plus B equals C? If I took this side plus this side and didn't square them, will it equal this side? No, it will not. There may be sometimes, I haven't done any research on it, I can't think of it off the top of my head, there may be a situation where that actually works, but not generally. You cannot say that this generally works, okay? But this thing right here actually does work. There is a little bit of proof on it on page 541 if you want to look at that. But right now for this lesson, for this video, I'm just trying to show you how to use the Pythagorean theorem and not really prove it for you. Let's do a couple examples. Okay, here's our first example. It's pretty straightforward. They give you both legs. If you want to, you could label them if it makes it a little easier for you. So you notice this is a leg, so I'll call that A. This is a leg as well, and I'll call that B. And this side right here is the hypotenuse. That's going to be the C in our Pythagorean theorem. If you want to put a C there, I guess you could. But let's write it down. So A squared plus B squared equals C squared. And let's just plug the stuff in. So, and it doesn't matter if the A goes first or the B goes first. It doesn't make any difference at all. But we'll do it in order. We'll go 15 squared plus 6 squared, and that equals C squared. So we work on that. Let's put that in our calculator. It's 15 squared, and then we'll go plus 6 squared. Some of these you can do in your head, but we'll just put it in the calculator anyway. And that's 261. So that's 261 equals C squared. Well, that's not how long this is. Now think about it. Please make sure that you look at your answer and see if it makes sense before you write the answer down. I've had students do this all the time, and they'll just write 261. But look, if you have a triangle and this is only 6 and this is 15, is there any way that this is going to be 261? No, of course not. So make sure you solve for C and not C squared. So how do we get rid of a squared? We take the square root of both sides, and C equals the square root of 261. This doesn't simplify. we'll just keep it the square root of 261. I would rather you keep it like this, to tell you the truth. I much would rather, I would, how did I say that? I would rather that you keep it the square root of 261, right? And not put it into your calculator. Now, if you wanted to, actually, I shouldn't even say if you wanted to, because I don't want you to, but some people would do this and put square root of 261 and get a decimal number. Now, the decimal number kind of makes sense, all right? It's around 16 point, what was it, 15? Yeah, so we'll say, we'll round it to, let's say 2 decimal places, 155, so that'll be 16. So 16.16. That would actually be acceptable, but for me, let's say no. I want you to keep it as a square root. And to tell you the truth, now that I think about it, we need to check 261 and see if that will actually simplify, because I believe it does. Let's if you're not really sure how to go about it, let's just think of some numbers that may possibly go into it. Well, it's an odd number, so you know that 2 and 4 doesn't go into it. So that doesn't work. Let's try 9. Let's just see if 9. Now, why did I pick 9 all of a sudden? Because I want to check to see if 4 goes into it, because the square root of 4 is 2. I want to see if 9 will go into it, because the square root of 9 is 3. So that would be the next on my list. Try 4, try 9. Okay, then you would try 25, and you go on like that. So let's just try 9. 261, and we'll divide that by 9, and we'll see if that comes out even. Oh, sure it does. Look at that. It's 29. So that means 9 times 29 is 261. So let's write it like that. 9 times 29 is the same thing as the square root of 261. Now, if I simplify that, the reason I picked 9 is because I knew I could take the square root of 9 and it comes out to a whole number. So the square root of 9 is 3, and your answer is 3 times the square root of 29. That is in simplest form. And that's how I want you to write your answers. Now, to tell you the truth, in the real world, you'd probably use a number like this, 16.16 or 16.2. In the real world, you would probably do that and put it into a calculator. But I'm telling you, there's a lot of teachers, even in college nowadays, they still want you to simplify the radicals. They want you to know how to simplify that. So I'm going to kind of make you simplify it. Not because they actually use these answers in real life. They would more likely use an answer like this. But I just want you to be prepared if in another course or another teacher makes you simplify the radicals. Let's do another example. Here's another right triangle, and you can tell by that little box right there. And we want to put it into the Pythagorean theorem. Now, this is where people get a little bit mixed up. Make sure that you're very careful on this, and you know which one are your legs and which one's your hypotenuse. In fact, I'm going to circle the hypotenuse so we can see it. How do you know which one is the hypotenuse? It's the one that's opposite the right angle. So here's the right angle. So this right there is the hypotenuse. So this must be the A and the B, and this has to be the C. A common mistake, and I almost hate to even tell you what the common mistake is, because some people will actually make the mistake if I just say it. But anyway, I'm going to say it anyway. The common mistake is that people just take the two numbers and use those as the A and B, and they always pick the variable as the C. You can't do that. Remember, the hypotenuse has to be the C. Make sure you do that. So this is the A, this is the B, so it's going to be A squared plus B squared equals C squared. It's very important that you set it up like this. Don't always just put the two numbers next to each other and add them up. Make sure that the hypotenuse always goes out here by itself. The one that's sitting there out by itself is always the hypotenuse. So let's solve for x now. So let's get 9 squared is 81. 11 squared is 121. We subtract 81 from both sides, and we get 40. X equals 40. Oh, sorry, not x equals 40. Sorry about that. X squared equals 40. And now we're going to take the square root of both sides. We take the square root of this side, take the square root of this side. So x equals the square root of 40. Always look to see if it simplifies. So where do we start first to see what goes into it? Start with 4. Does 4 divide into this? Well, absolutely it does. That's an easy one. So it's 4 times 10. Why did we pick 4? Because I could take the square root of 4. The square root of 4 is 2. And what's left over? See, that becomes a 2. And what's left over? A 10. You can't simplify the square root of 10 any further. So your answer is 2 times the square root of 10. This is how I want you to write your answer. I do not want you to put into a calculator and give me a decimal answer. I want it exact. And I may even say that on test or quiz. I can't remember. I think I might have. So when they ask for an exact answer, they're asking for a simplified square root type of an answer. Don't put it into a calculator and get a decimal. Now watch, if you actually came out with, let's say you did a problem and x was equal to 16, or square root of 16, all right? Don't leave it the square root of 16, simplify it. And what does that simplify to be? It simplifies to be 4, so you would absolutely leave it as a 4. All right, you get rid of the square root and you'd leave it as a 4. So you could put that into a calculator, I guess, but that's the simplified version if the answer came out to the square root of 16. This one doesn't, but you get the idea. Let's do another type of this, and this kind of leads you up to something here. As you saw in the other two examples that we did, sometimes your answers come out a little bit ugly. Sometimes, you get these weird square roots, and it just doesn't look very nice. But there are some times where you get some answers that come out real, real pretty. I'll show you the most basic one. Let's say that was 3, and this was 4, and I had to find x. I wanted to find what that was equal to. So let's do this very quickly. So I'd go 3 squared plus 4 squared equals x squared. That's 9 plus 16 equals x squared. Add them up. That's 25 equals x squared. Take the square root of both sides, and x equals 5. Now look at that. There was no crazy square root numbers in here at all. They all came out to nice whole integer numbers. When you have a situation like this, now it doesn't happen real often, to tell you the truth, okay? It just happens every once in a while. Since it only happens every once in a while, it's kind of special, and these are kind of special triangles, and we actually call these things Pythagorean triples. Pythagorean, spell it right, triples, because all 3 numbers come out to nice integer numbers, nice whole numbers. So this is commonly called a 3, 4, 5. Some people just say 3, 4, 5 triangle, but I'll call it a 3, 4, 5 right triangle. And that's really very, very helpful. A lot of times on standardized tests, like on the SAT or things like that, they'll work with Pythagorean triples, and sometimes it'll save you a lot of trouble. Instead of going through all this mess right here to figure out what this was, if you recognize that one leg is 3, the other leg is 4, the hypotenuse will always be 5. So that's really, really nice. Now watch, you could do it another way too. They could have told you that this was 5, and they might have not told you what that was, that side right there. We'll call it y. So if they had a situation like this, you could have set the Pythagorean theorem up. You could have gone y squared plus 4 squared equals 5 squared, done your math, and solved for y. And what would you come up with? You would actually come up with a 3. So it's a lot easier looking at this thing and saying, oh, it's a what 4, 5 triangle. Recognize it's a 3, 4, 5 triangle. Another cool thing about this is it doesn't have to just be 3, 4, and 5. You could do factors of 3, 4, and 5. For instance, if this was, I'll do it easy, 6 and 8, okay? Without doing Pythagorean theorem at all, knowing this Pythagorean triple right here, this 3, 4, 5 right triangle, you should be able to find this hypotenuse with doing very, very limited math. Because look at this. 6 is twice as big as 3. 8 is twice as big as 4. So guess what this is going to be? This is going to be twice as big as what? 5. And what's twice as big as 5? That would be 10. So a 6, 8, 10, right? Oops. Got a little ahead of myself. So that would be 6, 8, 10. Now, you don't have to memorize a whole bunch of these, but you can see if you have different factors involved right here, sometimes it reduces down to a 3, 4, 5 triangle, right? It's a larger triangle. This would be larger than 3, 4, 5, but it's in the same ratio and all that kind of stuff, and it's just bigger by a factor of 2. That can be very, very helpful sometimes. There's other Pythagorean triples, and they're listed on page 542. So let's just write down a couple that you may see from time to time. Now, you could always go back to the Pythagorean theorem and work these things out, but I tell you what, it's really nice to have some of these memorized. Makes things go a lot quicker when you're trying to get an answer, and it's a lot easier. Then you can move on to the next question, because you realize on standardized tests, time is definitely a factor. All right, so we had 3, 4, 5. Another one would be 5, 12, 13. So if this is 5, this is 12, this will be 13 right there. It's the same idea. I'm just going to list them out for you. Another Pythagorean triple is an 8, 15, 17. 8, 15, 17. Again, if they had an 8 here and a 15 here without doing any math at all, just knowing your Pythagorean triples, you would know that that would be 17. And here's another common, fairly common one, 7, 24, 25. And I'm sure there are more of these. This is the only ones that they list in the book, the only ones that I can think of off the top of my head. There could be more, but these are pretty important. So we'll list 3, 4, 5 up here with our little list. All right, so those are some common Pythagorean triples. It's not an exhaustive list, but there are common ones, and it really, really comes in handy when you're doing some of these. Let's do an example using a Pythagorean triple and just showing you that it's a little bit easier than just going through Pythagorean theorem every single time. Okay, here's one. Now, again, you could go through the straight-up Pythagorean theorem to get this answer, okay? You don't have to know Pythagorean triples, but it's just sometimes a little bit helpful. Let's take a look. I've got a 15 and a 12, and I'm trying to figure out what this side's going to be right here. With very limited math, we can actually figure out this thing if we know our Pythagorean triples. But let's take a look at 15 and 12. Is there a common factor between 15 and 12? Is there something that's evenly divided by both of these? Well, 3 is, isn't it? So 3 goes into this how many times? 5 times. 3 goes into this 4 times. Does that help us at all? Well, sure it does, because look, 5 is opposite the right angle. That's my hypotenuse. This is a leg, this is a leg. So it's a what, 4, 5 triangle. It's a 3, 4, 5 triangle, but it was what? 4 times 3, 5 times 3. So what's this going to be? 3 times 3, which is 9. So that's how we use the Pythagorean triple to figure out this side right here. Now, again, you could have gone through Pythagorean theorem, but sometimes those numbers are really big. Even if you can use a calculator, sometimes it's just time consuming. If you get this thing down right here, it'll save you a lot of time. Let's do another one. Okay, here's a right triangle. Remember, this stuff only works with right triangles. We could do Pythagorean theorem if we wanted to, but those numbers are a little bit big. I don't want to deal with those large numbers. Let's see, is there anything in common? That's what I would first look. Is there anything in common with both of these, a common factor? Well, 4 divides into both of those. 4 goes into 20 5 times. 4 goes into 48. What's that, 12 times? So let's take a look what we have in the pink color right here. We have a 5, 12. Do you remember what that Pythagorean triple is? It's 5, 12, what? 13. But my answer is not 13. X is not equal to 13. How did we get 48 from 12? How did we get 20 from 5? We multiplied by 4. So what am I going to do? I'm going to multiply, hold on just a second. Okay, I was just checking my math. I was doubted myself there. So 5 times 4, 12 times 4. So this is 13 times 4, which is, which is 52. So your answer is 52. Now, the title of our lesson was the Pythagorean Theorem and its converse. So what I want to do is, let's list this A, B, and C. Now look at this. You may think this is a right triangle. You're probably thinking, well, we've been talking about right triangles and it sure looks like one, but technically it's not a right triangle. And why not? Because it doesn't have the right angle symbol right here. But what if I was to do this? What if I said, and we'll use a Pythagorean triple just to make it easy, okay? What if I said that that side was 3, that side was 4, and that side was 5 right there? Now, I didn't tell you that this was a right triangle, but I did tell you the measures of the 3 sides. With that said, what do you think may be true about this I didn't want to say right. What do you think might be true about this triangle, this particular triangle? Well, you're probably right, okay? You're not probably right. You are right, I'm sure, what you're thinking. You're thinking that if I take this side, square it, take this side and square it, take the 2 shorter ones. You see that? I don't know this is the hypotenuse because I don't know that that's a right angle. But if I take the 2 shorter sides and add them up and then compare, and I'm sorry, let's say this again. If I take the 2 shorter sides, square them, and add them up, they should equal this longer side squared. So let's do that. And in fact, instead of going A, B, C, and I'll show you why I'm going to do this here in a little bit, but let's start with the C first. So if I take that C and I square it, that's the longest side, okay? C is going to be my longest side. Remember, I don't know it's a right triangle just yet, but if I take C, which is the longest side, and square it, and I compare it to the square of the sum of the squares of the other two sides, watch. If I compare it, I'm leaving a blank right here, okay? I don't know it's equal just yet until I actually do the math on it. So what am I going to do? I'm going to work it out. So that's 25, that's 9 and 16, and that's 25 still. And look, that's 25. So 25 is equal to 25, so that is equal. So if I take the longest side and square it, and it's equal to the sum of the squares of the two shorter sides, what kind of triangle do you think this is? You're right. It is a right triangle. So that's a test to see if it's a right triangle. So let's write this down. So if it's a right triangle, what must be true? This must be true. C squared must equal A squared plus B squared. That would be a right triangle. Now, this is kind of cool too. I'm not really going to prove this to you. Just take my word for it, I guess. What do you think we could do to these in order to make it an acute triangle? Now watch this. Now remember, C is the longest of the three sides, okay? And these are the shorter. All right, so you got three sides. These are the two shorter sides, and C is the longest side. So what I do is I take the longest side, which is C, I square it, and I compare it to the sum of the squares of the other two sides. But watch. In order to be a right triangle, these must be equal to each other. But in order to be an acute triangle, the longest side squared, the C squared, must be less than the sum of the squares of the other two sides. And that's kind of easy to remember because acute is less than 90. So this is less than. Make sure that you compare it with the C first and then the two sides over here. Now watch. What do you think then? I think you're getting the hang of this. What do you think would happen if you had an obtuse triangle? I would take that C squared and compare it to the A squared plus B squared, but what do you think must be true in order for this to be an obtuse triangle? Think you got it. It would be greater than. So if it's a right triangle, C squared would equal A squared plus B squared. If it was an acute triangle, C squared would be less than A squared plus B squared. And if it was an obtuse triangle, C squared would be greater than A squared plus B squared. Let's do a short little example here just to show you how this works. Okay, here's the kind of question they're going to ask on this converse of the Pythagorean theorem. It says, determine whether each set of numbers can be the measures of the sides of a triangle. So they're going to give you some numbers. So let's start off with 7, 14, and 16. These examples that I've been doing are right from the book if you want to look. And we want to take a look at those numbers and determine whether they can actually be the sides of a triangle. We did this in another chapter. How do you even know if you can form a triangle with those sides? Well, the first thing you have to do is take the two shorter ones, 7 plus 14, and it has to be greater than the longest side. Well, is it? Sure it is. That's 21, and that is greater than 16. So yes, it is a triangle. So I'm going to put yes. It is a triangle. All right, so we determined that, but there's two parts to this. It says, if so, if it's a triangle, okay, this definitely is a triangle. Classify that triangle as an acute triangle, a right triangle, or an obtuse triangle. Now, how do we do that? We don't just add them together. What we're going to do is we're going to take the C, the longest side. Which one is the longest side? It's 16. So I'm going to take 16, I'm going to square it, and I'm going to compare it to the sum of the squares of the two shorter sides. That means over here, I'm going to take the two shorter sides, 7 and 14, and I'm going to square them, and I'm going to add them up. And then I want to compare those numbers. So let's see what we get. Let's put it in the calculator. So let's click on 16 squared. 16 squared is 256. So I'm going to put 256 right here. Then I'm going to compare it to this number over here and see. I want to see if they're equal to each other, if this is less than this, or if it's greater than that. And that tells me what type of triangle I'm going to have. So let's take 7 squared and let's just add it to 14 squared and see what we get for that. That's 245. So that's 245. Now what's the relationship between 256 and 245? Well, 256 is greater than 245. So that means what type of triangle are we going to have? According to what we said a little earlier, this is an obtuse triangle. So there's two answers. Yes, it's a triangle, and it's an obtuse triangle. And it says justify your answer. This work right here, all this is justifying our answer. It's showing our work is what they're asking us to do. And that's all there is to it. If this number out here was less than the sum of the squares of the other two sides, it'd be acute. If it was equal, then it would be a right triangle. And that's pretty much it. I tell you what, let me do one more. Sorry, I know you want this to be over, but I think this is going to be helpful. Let's throw one out there where they give you some square roots, because some people have a little difficulty when they give you square roots. And 3 square root of 5. All right, first of all, let's determine, and make sure this works, okay. Let's determine if it's a triangle to begin with. All right, so let's just put it down. 2 square root of 3. Let's just figure out what that is. It's about 3.5. I'll just round it. That's around 3.5. I just want to find out what the lengths are first, because it's hard to add those up when they're not the same. Okay, this is square root of 3, square root of 2, square root of 5. So I'm just putting them in here just to see what it is. 4 square root of 2, and that's about 5 point, let's round it to 7, 5.7. 5.7. And let's take 3 square root of 5, 3 square root of 5, and that's about 6.7. So that's about 6.7. All right, so what we're going to do is we got to determine if it's a triangle to begin with. So we can kind of do this in our head pretty easy. Watch. These are the two shorter sides, 3.5 and 5.7. If I add them up, will they be bigger than 6.7? Sure, because 3 and 5 is 8 already. So we say yes, it is a triangle. It is a triangle. That was pretty easy to see. Now what we want to do, this is what I was really getting at. Now what we want to do is see if it's acute, obtuse, or right. So what do? We take the longest side first. Which one's the longest one? This one right here. 3 square root of 5, and we have to square it. Now look what I did. I put it in parentheses. Now I'm going to compare it to the sum of the squares of the two shorter sides. So I'm going to take 2 square root of 3. I'm going to square that. And then I'm going to add it to 4 square root of 2, and I'm going to square that. And it looks complicated, but it's not as hard as it looks. Watch. Let's square everything in here. If we square 3, we get a 9 times. Now, this is what a lot of people get confused about, but it's actually easier than squaring a 3. What's the square root of 5 squared? Well, it's just a 5. That's all it is. Okay, the square takes away the square root. See, told you it was easy. So 9 times 5 is 45. And I'm going to compare that to this. So let's do this. Let's square everything in here. 2 squared is 4. Square root of 3 squared is 3. And that's going to be a 12. But I got to add it to this. 4 squared is 16. And then square root of 2 squared is 2. That's 32. Let's add them up. That would be what? 44? So what I'm doing is I'm comparing 45 to 44. So what's true about 45? Well, it's greater than 44. So again, this triangle is obtuse. Now again, like I said, if this left number was if it was less than the right number, then it would be acute. If they were exactly equal to each other, then it would be right. But in both of these examples, they just happen to come out to be obtuse. All right, I think that's pretty good. I think we're good for that. So good luck with that lesson.